Hi guys, welcome to another snow day lecture today. We're gonna look at the assembling the ideal gas law equation to stay on schedule with what we were doing in class yesterday. And then there's 4 homework problems that I'll kind of walk you through and set up at the end of this video. And then those 4 homework problems will be due tomorrow. Please have them on a separate sheet of paper, show your work, ready to be handed in tomorrow. And then the quiz will be on Friday as scheduled. Let me just double check something as long as I'm on this screen. Okay, we should be good. It is recording. And other than that, I think we're good to go for the next couple of days. So starting today with assembling the ideal gas law equation, there's 4 parts to it. There's 4 measurements that we talked about in assembling or talking about how we describe gases. So we're going to look at how volume relates to moles, temperature, and pressure to get some mathematical relationships. And then we're going to assemble this into one equation. You'll see how this sort of flows together. So the first is that volume is directly proportional to amount. So amount of gas being moles of gas. So, we can express this basically as, volume is equal to, or they're both in the numerator on either side of this equation. They are directly proportional to one another. Okay? So they're both directly proportional to one another. They both appear on the numerator on either side of the equation. And there's Anders sneaking in the screen behind us. So I'm going to say hi to the chemistry guy, kids. You can't just show them a football. You got to put your face in the screen. There he is. All right. Say wave hi. They can't see you. All right. There we go. So now again in this situation, temperature and pressure are going to be held constant in this relationship because temperature and pressure can play a role in fluctuating the volume, which we'll look at in just a minute. So in the relationship over here in the graph, as volume and moles are the 2 variables here. As we increase the number of moles, the volume is going to proportionally increase on a linear relationship. So, which makes sense. Like if you blow up a balloon, the more moles that you blow into that balloon, the larger the volume in that balloon is going to get. Okay. Second relationship, volume is directly proportional to the absolute temperature. Again, absolute temperature refer to the temperature in Kelvin. This relationship is sometimes called Charles's law. So again, in the relationship, volume is equal to or directly proportional to the temperature. They're both in the numerator on either side of the equation. Again, holding the other 2 variables constant, moles and pressure, when we're looking at this relationship, because if we had differing number of moles or pressure, that would affect the volume. So we're isolating volume compared to temperature. Okay. So in the relationship, as you increase the temperature, right, in Kelvin, the volume is going to directly proportionally increase as well in a linear relationship. Okay. Which kind of makes sense again, when you think about like the air in your car tires or your vehicle tires or your bike tires. If the temperature increases, volume increases, right? If temperature decreases, volume decreases a little bit, right? So we talked about cold weather causing your tires to look like they're flat. The volume goes down a little bit. That's partially because of the temperature decrease. Now you'll see the dots here that I have. Okay. The reason why this line is not completely solid is because and we're going to talk more about this later. Excuse me, as gases decrease in temperature, eventually what happens is their volume decreases to a point, and then gases will start to transition from a gas to a liquid. Okay? So when you reach extremely cold temperatures, gases will transition their physical state from a gas to a liquid. So when we're talking about extremely low temperatures, we really can't use this relationship very well because it's no longer really a gas. It's transitioning into a liquid. And that's why you're going to see that the ideal gas law is good, because it's talking about ideal situations. at extremely low temperatures, the ideal gas law breaks down. We'll have some more discussion about that in a little bit, but also later on as we round out this unit. Okay. The third relationship is where volume is going to be now inversely proportional. So volume is inversely proportional to the pressure. This is sometimes called Boyle's law. Okay? So in this case, volume is in the numerator on this side, pressure here is in the denominator. So it's an inversely proportional relationship. Okay? So volume is equal to 1 over pressure. Excuse me, guys. So it's an inversely proportional relationship. Again, the other two variables are being held constant. What does this ultimately look like on the graph here? Okay, is volume here on the x-axis. Okay, so y-axis, sorry, and then pressure on the x-axis. If you are ever increasing the pressure, right, it looks like this. I think it's called a, what is it, a parabolic curve? Okay, in this inversely proportional relationship. Extremely low pressures equate to really high volumes. Extremely high pressures equate to really low volumes of a gas, which kind of makes sense. I placed this red dot over here too because if you look at this, again, eventually as this line, okay, as it reaches extremely high pressures, what will happen is that the volume of the gas will continue to decrease, but eventually it reaches a certain limit. Because at extremely high pressures, okay, what happens is again, gases will start to transition from a gas to a liquid again, okay? So again, the ideal gas law doesn't work at extremely high pressures because gases start to transition or change phase from a gas to a liquid. So when we're talking about the ideal gas law, we need to be talking about sort of pressures that are sort of in this area, right? We're talking about, going back a slide, temperatures that are sort of in this area. For extremely low temperatures, it doesn't work, okay? The ideal gas law. All right, so now moving on. So we have the three relationships. Volume is directly proportional to moles. Volume is directly proportional to temperature. Volume is inversely proportional to pressure, right? So if we have an expression like this where we have three variables equaling the same thing, N, T, and 1 over P equals V, okay, we can smash them all together and create one combined equation, right? So, but there's an issue with this, if you guys notice, right? I mean, what we're saying is volume, which is liters, is equal to moles times Kelvin over atmospheres. Well, the units volume liters doesn't equal moles Kelvin over atmospheres. So we have to take care of this issue. While the relationship holds true, the proportionality of the three relationships that we looked at on the previous 3 slides holds true, the equation has to be adjusted to be able to allow for us to make this mathematical statement true. How do we do that? Okay, let me go to the next slide. We add what's called a constant, and that's what a constant does, is it makes it so what is a known mathematical relationship can actually be manipulated and used, okay? So volume is equal to the constant, it's called the gas constant, times NT over P, right? So the gas constant is, right, the R value. We use R to represent the gas constant. It's 0.0821 liters times atmospheres over moles times Kelvin. And you'll notice in the units on the constant, it includes all 4 units, okay? All 4 units of the 4 ways that we're describing gases, right? Now that's important because the constant then allows us for, when we assemble our equation, on the next slide, okay? When we assemble our equation, anytime we're using this equation, the constant gives us the ability to eliminate the units and end up in the units of whatever we're trying to solve for. So sort of foreshadowing to what we're end up doing is you're going to be given some problems in just a minute where you're going to get given 3 of the 4 variables. So either P, V, N, or T, okay? You're going to be given 3 of the 4 variables and you're going to solve for the missing variable. So again, real quickly back to the ideal gas law equation though before we get into that, what I just talked about. So that we have that ideal gas law constant, or the gas constant. It's the R value, plug it in here, right? And there's the gas law equation. But in the world of chemistry and the world of using the ideal gas law equation, they like to rearrange it from this sort of numerator denominator nonlinear equation into a linear equation. Excuse me. So all they do is they're going to multiply both sides by the pressure, okay, to get rid of pressure and put pressure in the numerator on this side. Rearrange the R's and the N's and T's a little bit, and we have PV equals nRT. Sometimes it's called the Puvnert equation. Kind of a dumb way of saying it, but it works. Okay. So the Puvnert equation is the ideal gas law equation. Again, pressure is in atmospheres, volume in liters, N is moles. Needs to be in, amount needs to be in moles. T is the temperature in Kelvin, and then the R value is constant. You'll always have the constant, 0.0821 liters times atmospheres over moles times Kelvin. Okay, so we're at the PV equals nRT or Puvnert calculations. Again, just reminding you, we just said this. Okay, volume in liters, pressure in atmospheres, amount in moles, temperature has to be in Kelvin when we plug it into the equation. Your R value is 0.0821 liters times atmospheres, moles times Kelvin. And that'll be the same for when we're using the ideal gas law in this form, okay? In your book, if you look at this table on page 119, 5.1, table 5.1, there are some other R values that are used for the ideal gas law constant, or the gas law constant, and we'll talk about those later on, okay? For now, we're only using, so this is later. For now, we're only using this form of the gas constant in solving and using the Puvnert equation. All right, so again, you guys can access your textbook as a sort of a point of reference for some of these problems. Okay, here are the 4 example problems that are your homework for tomorrow. Right now, I'm going to flip to the screen, and then you guys, I'm going to talk you through a little bit. Okay, so you got we're going to be working with this the ideal gas law equation, ideal gas law equation. You're given the moles, the pressure, and the volume. Okay, given the moles, the pressure, and the volume, and they're already in the units that you need it to be in. So you can immediately plug these into the equation and solve for the temperature ultimately. The temperature will be solved for in Kelvin. Make sure that you show your work, show all units being canceled as you solve for the temperature as you plug the values into this equation. So that's question number 1. Here's question number 2, again using the same equation. You're given moles of O2 gas. It's at 753 millimeters of mercury pressure, so its pressure, okay, is not in atmospheres. You got to convert it to atmospheres before you can plug it in. You're given the temperature in Kelvin, so it's already in Kelvin, so you don't have to do any converting. Your job is to figure out what is the volume in liters, but I also want you to do one extra conversion at the end. Convert liters to cubic meters. You have your conversion factor from class the other day. So again, this is question number 2. You're ultimately solving for the volume, but then secondarily converting the volume from liters to cubic meters. Third question. In this case, you're given 33 grams of CO2 gas. It's not in grams now, it's not in moles now, it's in grams. So you have to convert from grams to moles to be able to plug it in here. You're given the volume in liters, so you can plug it right in for the volume. You're given the temperature, and this time it's in Celsius. So you got to convert it from Celsius to Kelvin before you can plug it in here. You've got your ideal gas law constant taken care of. You're solving for the pressure. Now when you spit it out of the equation, the pressure is going to be in atmospheres. I want you to solve for the pressure in atmospheres, but then additionally, I want you to do one extra conversion and convert atmospheres to millimeters of mercury. Okay. Question number 3, the final question. Oops. In this one, again, still using the same equation, the Puvnert equation. In this case, you're going to be solving for ultimately moles, and then you convert to grams. But what are you given? You're given the pressure in atmosphere, so it's good to go. You can plug it right in for pressure. You're given the volume in liters. You can plug it right in for the volume. Okay. You're given the temperature. In this case, it's Fahrenheit. So you're going to have to convert the temperature from Fahrenheit to Celsius, and then from Celsius to Kelvin before you can plug it in here. Right? You've got your ideal gas law constant. You can solve for N being the number of moles. So you're going to figure out the number of moles of O2 gas at 1.3 atmosphere pressure, 4.1 liter volume, and 72 degrees Fahrenheit. Once you get moles, though, you're going to do one extra set of conversions at the end to go from moles of O2 to grams of O2. And again, this is just a mole road problem at the end. Okay. All right. So that's the fourth and final problem. Again, these 4 problems, do it on a separate sheet of paper, name, hour on it. You guys will hand this in as homework tomorrow, right? And then the last thing, I'll just flip to this slide so you guys sort of understand some things, some fair game stuff that's going to help you prep for Friday's quiz on the ideal gas law equation and the use of it. And obviously tomorrow in class we'll talk about these 4 homework problems. We'll look at some examples. But some places to look. Example 5.3 in your book, chapter problems 1 and 3, okay, which are assigned to you, part of your homework for later on with the big homework problems that are due. And then number 2 is also a good one too. The nice thing about this one is that it has the answer in the back of the book. Okay, so the solution for. So again, if you're looking for some extra practice, 1, 2, and 3 in the chapter problems are good ones. And then realize that this is the quiz cutoff point for Friday's quiz on using the ideal gas law equation. So the problems that you'll be presented will be like that of, basic conversions among the different variables that we use for gases to describe them. Using the ideal gas law equation, either having to convert into or convert out of, like the 4 problems that we just presented to you for your homework that is due tomorrow. Okay. And then on Friday, then tomorrow, we'll probably, after we kind of look at some examples, we'll probably maybe end up starting a little bit of talking about final and initial stage problems or initial and final stage problems. You don't need to worry about writing this down, but we'll get to this tomorrow and then into Friday after the quiz. Okay. All right. That should be it, guys. I'll be available to answer any questions via email. But 4 homework problems due tomorrow. Use your book if you need to access another source. Hopefully everything's good to go, and we'll see you tomorrow. Thanks, guys.